I've been revisiting microcomputer fundamentals. Can we start with the CPU's role in instruction execution?
Absolutely. The CPU fetches instructions from memory, decodes them via the control unit, and executes them using the ALU. Each step, fetch, decode, execute, is part of the instruction cycle. How do you see pipelining affecting this process?
Pipelining overlaps stages of multiple instructions to boost throughput. But doesn't that complicate hazard detection?
Exactly. Data hazards occur when instructions depend on prior results. Solutions like forwarding or stalling the pipeline help. What about branch prediction's role here?
Branch prediction guesses the outcome of conditionals to keep the pipeline full. But mispredictions waste cycles. How do modern CPUs mitigate this?
Advanced algorithms like dynamic branch prediction use history tables. Some even employ machine learning. Let's shift to memory. Why is hierarchy critical?
Memory hierarchy balances speed, cost, and capacity. Registers and cache are fast but small. RAM is larger but slower. How does cache coherence play into multi-core systems?
In multi-core setups, each core has its cache. Coherence protocols like MESI ensure data consistency. Now interfacing, what's your take on memory-mapped I/O versus port-mapped I/O?
Memory-mapped I/O treats peripherals as memory addresses, simplifying programming. Port-mapped uses dedicated instructions. Which is better for low-resource systems?
Port-mapped conserves memory space but requires specific instructions. Memory-mapped is more flexible. Let's discuss interrupts. How do ISRs handle concurrency?
Interrupt service routines pause the main program. Priorities resolve conflicts. But what about nested interrupts?
Higher priority interrupts can preempt lower ones. The stack stores the CPU state for resumption. Speaking of efficiency, how does DMA reduce CPU overhead?
DMA controllers handle bulk data transfers between peripherals and memory. The CPU only initializes the transfer. What are the trade-offs?
DMA frees the CPU but adds complexity. Bus contention can arise. How do arbitration protocols like round-robin help?
Arbitration prioritizes devices fairly. Now, embedded systems. Why are microcontrollers dominant there?
MCUs integrate CPU, memory, and peripherals on one chip, ideal for cost/power-sensitive applications. How do GPIOs interface with sensors?
GPIO pins can be programmed as input or output. Pull-up resistors stabilize signals. What protocols optimize sensor communication?
I2C for low-speed, multi-device setups. SPI for high-speed, point-to-point. What about UART's role in legacy systems?
UART's simplicity makes it ubiquitous for serial communication, even in modern IoT. But it lacks built-in addressing. How does RS-485 handle multi-drop?
RS-485 uses differential signaling for noise immunity and supports up to 32 devices. What's your view on USB replacing legacy serial ports?
Let's start with the CPU's fetch, decode, execute cycle. How do modern microprocessors optimize this?
They use pipelining to overlap stages. For example, while one instruction is being executed, the next is decoded, and another is fetched. But hazards like data dependencies can stall the pipeline. How do you handle that?
Forwarding units bypass stale data by rerouting results directly to dependent instructions. But for control hazards, branch prediction is key. Static versus dynamic, what's your take?
Static prediction assumes branches, like loops, are taken, while dynamic uses history tables. Modern CPUs like ARM Cortex-A use 2-bit saturating counters for accuracy. What about speculative execution?
Speculative execution guesses branch outcomes and executes ahead. If wrong, it flushes the pipeline. It's powerful but introduces vulnerabilities like Spectre. How do we mitigate that?
Hardware fixes like partition buffers, or software mitigations like compiler barriers. Let's shift to memory. Why is cache hierarchy critical?
Caches reduce latency, L1 for speed, L2 per liter 3 for capacity. But associativity matters. Direct mapped versus fully associative trade-offs?
Direct mapped has lower latency but higher conflict misses. Fully associative avoids conflicts but is slower. Most CPUs use set associative as a balance. What about NUMA in multi-socket systems?
NUMA, Non-uniform memory access assigns local memory to each CPU socket, reducing contention. But programming NUMA-aware code is tricky. How do OS schedulers handle this?
They pin threads to cores near their memory. Now, interrupts. Why are vectored interrupts better than polled ones?
Vectored interrupts let devices specify their ISR address, saving time. Polling wastes cycles checking all devices. But how do priorities work?
The interrupt controller, e.g., APIC, assigns priorities. Higher priority interrupts preempt lower ones. What about shared IRQs in legacy systems?
Shared IRQs require the ISR to check all possible devices inefficient. MSI, message signaled interrupts, in PCIe solves this by using memory writes. How does DMA improve I/O?
DMA offloads data transfers from the CPU. For example, a network card uses DMA to write packets directly to RAM. But cache incoherence can occur. How's that resolved?
Either the CPU invalidates cache lines, or the DMA uses coherent buffers. What's the role of a scattergather list in DMA?
It lets DMA transfer non-contiguous memory blocks in one operation. Crucial for modern storage and networking. Let's talk embedded systems. Why use microcontrollers over microprocessors?
MCUs integrate RAM, ROM, and peripherals, ADC, PWM, on chip, reducing cost and power. But they're less powerful. How do you handle real-time constraints?
RTOS schedulers like rate monotonic prioritize tasks by deadline. Watchdog timers reset the system if tasks stall. What about firmware updates in embedded devices?
Over-the-air, OTA, updates via secure bootloaders. Dual bank flash allows writing to one bank while running from the other. How do interfaces like I2C and SPI differ?
I2C uses two wires, SCL/SDA, with addressing, ideal for multi-device buses. SPI uses four wires, MOSI/MISO/SCKCS, for faster point-to-point transfers, which is better for sensors.
I2C for simplicity, SPI for speed. But what about bus contention in I2C?
Arbitration. If two devices transmit, the one sending a 0 overrides 1. The loser retries later. Let's discuss UART. Why is it still used?
UART's simplicity, no clock signal, just start/stop bits. Great for debugging or low-speed links. But no error correction and broadcast. How does RS-485 improve on -232 rupees?
RS-485 uses differential signaling for noise immunity and supports multi-drop, up to 32 devices. Now, USB. How does enumeration work?
The host detects a device, resets it, assigns an address, and queries descriptors to load drivers. What's the role of endpoints in USB?
Endpoints are buffers for data types. Control, bulk, isochronous. Now storage. Why is NVMe replacing SATA?
NVMe uses PCIe lanes for higher bandwidth and lower latency. SATA's AHCI protocol has queuing limits. How do SSDs handle wear leveling?
The FTL, flash translation layer, remaps logical blocks to physical ones, spreading writes evenly. What's the impact of QLC NAND on endurance?
QLC stores 4 bits per cell, increasing density but reducing write cycles, mitigated by over-provisioning and caching. Let's shift to GPUs. How do they differ from CPUs?
GPUs have thousands of cores for parallel tasks, e.g. shaders. CPUs focus on single-thread performance. What about heterogeneous computing?
Systems like ARM's big, little pair high-performance and efficiency cores. Also, accelerators, e.g. TPUs, for specific workloads. How do cache coherency protocols scale here?
Snooping-based protocols, e.g. MESI, work for small cores. Directory-based scales better for large systems. What's your view on RISC-V's impact?
RISC-V's Open ISA disrupts proprietary ARM/x86 dominance. Custom extensions allow domain-specific optimizations. How secure is it?
Security depends on implementation. Physical attacks like side channel remain a threat. Let's discuss IoT. How do edge devices handle processing?
Edge computing filters data locally, reducing cloud dependency. Microcontrollers with ML accelerators, e.g., TensorFlow Lite, enable on-device inference. What protocols dominate IoT?
MQTT for lightweight messaging, COAP for RESTful services, LoRaWAN, and NB-IoT for low-power WAN. How do you secure IoT edge nodes?
Hardware-based TPMs, secure boot, and over-the-air encrypted updates. But resource constraints limit crypto options. What's next for microcomputers?
Quantum microcontrollers, photonic computing, and AI-integrated silicon. Also, 3D stacked chips for density. How do you see RISC-V shaping embedded systems?
RISC-V will democratize custom silicon. Companies can build domain-specific cores without licensing fees. But toolchain maturity lags behind ARM. Closing thoughts?
The future lies in specialization. Microcomputers tailored for AI, automotive, or biomedical applications. Efficiency and security will drive innovation.
Let's explore RTOS scheduling. How does rate monotonic scheduling, RMS, guarantee real-time deadlines?
RMS assigns higher priority to tasks with shorter periods. As long as CPU utilization is below approximately 69%, deadlines are met. But what about aperiodic tasks?
Aperiodic tasks use a sporadic server, a budgeted time slice. But how do you handle priority inversion in RTOS?
The priority inheritance protocol temporarily raises the priority of a low-priority task holding a resource. Now, cache coherency in multi-core MCUs. How's it managed?
Snooping-based protocols like MESI track cache lines. Write-back caches reduce bus traffic but complicate coherence. What about non-cacheable memory regions?
Non-cacheable regions are used for DMA buffers or memory-mapped I/O to avoid stale data. Let's shift to RISC-V. How do custom extensions work?
RISC-V's modular ISA lets you add custom opcodes for domain-specific tasks like AI acceleration. But toolchain support?
You'd need to modify the compiler, e.g. LLVM, to recognize new instructions. What's an example use case?
Cryptography extensions for AES-NI style acceleration. Now, quantum microcomputers. How do qubits interface with classical systems?
Cryogenic control circuits convert quantum states to digital signals. But error rates are high. How's error correction handled?
Surface code error correction uses topological qubits, but it's resource-intensive. Let's return to embedded systems. How do watchdog timers improve reliability?
They reset the system if the software hangs. Windowed watchdogs even detect early triggering. What about brownout detection?
Brownout detectors monitor voltage dips and trigger safe shutdowns. Now, GPIO. How do you debounce a mechanical switch input?
Use a hardware RC filter or software delays to ignore transient spikes. What's the role of alternate function modes in GPIO?
They let pins double as SPI2C interfaces. Now, CAN bus. Why is it dominant in automotive systems?
CAN's differential signaling resists noise, and its arbitration ensures critical messages, e.g. brakes, get priority. How do FD variants improve speed?
CAN FAD increases payload size and byte rate, but requires updated controllers. What about security in automotive networks?
SecOC, Secure Onboard Communication, adds max to messages. Now, PCIe. How do lanes scale bandwidth?
Each lane is a serial link. X16 means 16 lanes. Gen 4 doubles Gen 3's 16 GTS to 32 GT south per lane. How do root complexes manage devices?
The root complex enumerates devices during boot, assigning memory and IRQs. What's the role of TLP, transaction layer packet?
TLPs carry read/write requests, completions, or messages. Now, NVMe over fabrics. How does it extend storage networks?
It allows NVMe commands over RDMA or fiber channel, enabling hyperconverged infrastructures. Let's discuss FPGAs. How do they differ from MCUs?
FPGAs are reconfigurable hardware. MCUs run fixed software. FPGAs excel in parallel tasks but consume more power. How do HLS tools bridge the gap?
High-level synthesis compiles C/C++ to FPGA bitstreams, simplifying development. What about eFPGAs and SoCs?
Embedded FPGAs provide customizable logic blocks alongside CPU cores. Now, photonic computing. How could it revolutionize microcomputers?
Photonic chips use light for data transfer, reducing latency and power. But integrating lasers with silicon is challenging. What's your take on 3D ICs?
3D stacking with TSVs through silicon vias boosts density and shortens interconnects. Heat dissipation is the hurdle. Let's talk security. How do TPMs work?
Trusted platform modules store cryptographic keys and perform secure measurements. What about side-channel attacks on MCUs?
Power analysis or timing attacks can leak secrets. Mitigations include constant time code and noise injection. How do secure enclaves like ARM Trust Zone help?
Trust Zone partitions the CPU into secure and non-secure worlds, isolating sensitive code. Now, what's next for RISC-V?
RISC-V will expand into hyperscale data centers and space-grade hardware. Open-source verification tools will mature. Closing thoughts?
The convergence of specialized silicon, open standards, and quantum leaps will redefine microcomputers. The key is balancing innovation with robustness.